and in this video I am going to explain my project real-time FPGA accelerated object detection and counting system using the PYNQ-Z2 board. This project uses both PS and PL of the FPGA board working together to detect objects in real time using a USB camera. So let me start from the beginning and explain everything step by step. So first let me tell you about the board I use. This is the PYNQ-Z2 board. What makes this board special is that it has two parts on the same chip. One is the PS, which is a dual core ARM Cortex-A9 processor, and the other is PL, which is basically the FPGA fabric. The reason I choose PYNQ-Z2 is because it supports Python programming directly on the board through Jupyter Notebook, and it allows you to communicate between the ARM processor and the FPGA fabric using a protocol called AXI DMA. This makes it perfect for project where we want to do hardware software co-design, meaning some tasks run on the processor and some run on the FPGA. And on the hardware side, I used Vivado from Xilinx to design the FPGA logic and generate the bitstream. A bitstream is the file that programs the FPGA fabric. On the software side, the board runs PYNQ version 2.7, which is flashed on an SD card, and I wrote all my Python code in Jupyter Notebook, which runs directly on the board. Now let me explain what I designed in Vivado. This is my block design. When you look at it, you will see several IP blocks connected together. The first and most important thing is the Xilinx processing system. This represents the ARM processor. I configured it to enable the HPO port, which is the high performance port. This port gives a high bandwidth direct connection between the ARM processor and DDR memory, which is needed for data transfer. And the second block is AXI DMA. This stands for Advanced Extensible Interface Direct Memory Access. This is the main communication block between the PS and PL. It has two channels, MM2S, which sends data from processor memory to the FPGA, and H2MM, which receives data back from FPGA to processor. The third block is AXI4 Stream Data FIFO. This FIFO is connected between the output of DMA and the input of DMA, creating what we call a loopback. So data goes from processor to FPGA, passes through the FIFO and comes back to the processor. This loopback design proves that the PS and PL are actually communicating through real hardware. Then there are two AXI interconnect blocks which acts as bus routers. They connect the DMA control port to the ARM's GP0 port and the DMA data ports to the ARM's HPO port. There is also a processor reset system block which handles clock and reset signals for the whole design, and an XL concat block which combines the DMA interrupt signals and sends them to the processor. After placing all these blocks, I ran connection automation in Vivado, which automatically wired all the clocks, resets and buses. Then I validated the design and created an HDL wrapper and generated the bitstream. This process took around 15 to 30 minutes. After it finished, I got two important files, a .bit file which is the bitstream and a .hwh file which is the hardware handoff file. These two files together are what PYNQ needs to load the design onto the FPGA. Important part: how exactly does the ARM processor communicate with the FPGA fabric? First, I loaded the bitstream using PYNQ's overlay class. This programs the FPGA fabric with my Vivado design and gives Python access to the AXI DMA block. And then for each video frame, I allocate two special memory buffers using PYNQ's allocate function, one input buffer and one output buffer. These buffers are physically contiguous in DDR memory, which is a requirement for DMA to work. Then I copy the frame data into the input buffer and tell the DMA to start the transfer. The send channel takes the data from processor memory, sends it over the AXI bus into the FPGA fabric. where it passes through the FIFO loopback and receive the channel, brings it back from the FPGA into the output buffer in processor memory. Then I call wait on both channels to make sure the transfer is complete before moving to the next step. Now here there was a problem I faced. The full camera frame is 640 by 480 pixels with 3 color channels, which is 9,21,600 bytes, but the AXI DMA in my design has a buffer limit of only 16,383 bytes, so I could not send the full frame through DMA. The solution I used was to resize the frame to a small 64 by 64 grayscale thumbnail before sending. This is only 4096 bytes, which is well within the limit. The full frame is still used for object detection, only the thumbnail goes through DMA to demonstrate the PS and PL. You can see these YOLOv3 files. These are the files I have used for my project. Originally, I planned to use YOLOv5 Nano in ONNX format because it is a very small and modern model, but I faced two problems. First, the library needed to run ONNX models called ONNX runtime does not have a pre-built package for ARM 32-bit architecture, which is what PYNQ-Z2 uses. So I simply could not install it on the board. Second, when I tried loading the YOLOv5 and ONNX file using OpenCV, it failed because YOLOv5 uses float 16 data type for its weights, and OpenCV 4.2 on PYNQ only supports float 32. So I switched to YOLOv3-tiny. This model uses the classic darknet format, a .cfg file for the network architecture and a .weights file for the trained weights. OpenCV 4.2 has full native support for this format, so no extra library installation was needed at all. YOLOv3-tiny is also designed specifically for speed on low power and embedded devices. It takes a 416 by 416 pixel input image and can detect 80 different object classes from the COCO dataset. Things like person, bottle, laptop, chair, cup, mouse, keyboard, and so on. Since the PYNQ board had no internet connection, I downloaded the CFG and weights files on my PC and uploaded them to the board through the Jupyter file browser. The weights file is about 34 megabytes. I set the confidence threshold to 0.15, which means the model reports any detection it is at least 15% confident about. I also used non-maximum suppression with a threshold of 0.30 to remove duplicate overlapping bounding boxes. Walk you through the complete flow of the system for each frame. The USB camera captures a frame at 640 by 480 resolution using OpenCV, and then I apply CLAHE enhancement on the frame. I added this because my testing environment had a bright window in the background which was causing backlit scenes. The person and objects appeared too dark for the model to detect. CLAHE fixes this by improving the local contrast of the image without overexposing the bright areas. A 64 by 64 grayscale thumbnail of the frame is sent through the AXI DMA to the FPGA fabric and received back. This is the PS and PL communication happening in real hardware. And then the full enhanced frame is passed to YOLOv3-tiny running on the ARM CPU through OpenCV DNN. The model processes the frame and outputs detection results. And then the detections are filtered by the confidence threshold and NMS. Then green bounding boxes are drawn on the frame with the object label and confidence score. And then the result is saved as JPEG image in the Jupyter folder, which I can open and view directly in the browser. And I also added a label remap to fix some wrong detection. For example, my dark steel water bottle was being detected as waste because of its shape and color. So I added a correction. Whenever the model says waste, the code relabels it as a bottle. Similarly, TV gets relabeled as laptop and bowl gets relabeled as cup. The system prints a live summary for every frame showing the frame number and what objects were detected, so you can monitor it in real time from Jupyter. So now let us see how it works. Initially, we ran the code and the model is loaded now, and the camera starts detecting the objects now. See, it detected 4 objects: laptop and a person and a keyboard and a chair for the first frame. And for the second frame, it got one chair and the keyboards and a laptop. And for the third frame, it detected 5 objects: chair, keyboard, laptop, person, and another keyboard of the laptop. And for the fourth frame, it got 3 objects: keyboard, and the laptop. The objects get decreasing because the light is little bit low here. And for the fifth frame, it got chair, keyboard, and the keyboard of laptop, and a person. So it goes on up to 30 frames, and for each frame, a max of 8 objects can be detected by the camera. Thank you.